Feckety, Logan Parker, and a whole crew of Colby students that have been working on all 7 lakes all summer. So they've probably collected about 500,000 data points for us so far, and we're doing that every year. And a crew is expensive. They want to get paid, and a lot of this work was started with a generous grant from the National Science Foundation, but that's been supplemented by the Bill and Joan Alfond Foundation, Fluid Imaging, which is the company that builds the flow cam that we're using at the Maine Lakes Resource Center. So that's a Maine-based company that's helping us identify plankton. Colby College is paying for 3 of the interns every summer. The BRCA, the MLRC, and then of course Tom Klingenstein, who's been paying for a number of those students every year. So this is the crew that makes this work possible. And I want to talk about sort of the challenges for the lakes. I'm going to begin with the cautionary tale, which is East Pond. Right, so this is a Google map of East Pond and North Pond. I think most of you have seen these images. The green is because the lake is in full bloom. It's black on North Pond because you can actually see all the way to the bottom of the lake. And our job is to keep all of our lakes looking like this and not like that. Okay. This is caused by the internal load of phosphorus coming off the bottom of East Pond. And I just talked to Mel, and East Pond is sort of looking like that right now. So if you want to see what we're trying to head off, go over to the East Pond boat launch, give it about a week, and then you'll really see what we're worried about. So this is the cautionary tale. The cautionary tale is that East Pond changed rapidly. This is a Secchi disc. You lower it down into the water column, and the deeper it goes, the clearer the water. In the 70s, the Secchi transparency on East Pond was about 4 meters. Not as clear as it is currently on Great Pond and Long Pond, but it was quite clear. And then all of a sudden something happened in 1988. The lake tipped. And the water quality went from averaging between 3 and 5 meters to going between 7 and half a meter. And so the lake now is very clear for a good part of the summer, but then all of August and September, it looks like, well, not quite that bad, but it can get that bad. That's a Secchi transparency of about half a meter. Again, our job is to keep that from ever happening. Right? So success is never letting any of the other lakes get to that point, and quite frankly, success is to reclaim East Pond so that that's no longer happening on East Pond. All right, so here's the ABCs of what's happening in the lake. So A, we have the surface of the lake. And the surface of the lake is warmed by the sun. And you can go out in the lakes right now, it's about 75 degrees. And this is the epilimnion, the top of the lake. It's warm, and in a pristine lake, it has low nutrients. Why does it have low nutrients? Because there's a balance between the inflow of nutrients and the outflow of nutrients. And the benchmark here is about 8 parts per billion. That's a good phosphorus number for a pristine lake. So surface is warm, and then there's a transition where the surface water and the deep water intersect, and that's called the thermocline. And that thermocline acts as a barrier for mixing. Warm water floats on top, it's less dense. Cold water is at the bottom, it's more dense, and there's this distinct boundary between the two. So the B in the lake is the hypolimnion, or bottom of the lake, and in a healthy lake, it's cold. And because it's cold, it holds a lot of oxygen. And so the oxygen profile in a healthy lake actually goes from about 8 parts per million in the surface, and it increases with depth, and that's good. So that's Sebago, that's Moosehead, that's Rangeley Lake. Those are all good examples of relatively pristine lakes. And then the C in our lakes is the sediment. And the sediments are what capture the nutrients and hold on to the nutrients. And the 2 elements that capture the nutrients are aluminum and iron. And in a healthy lake, there's about 10 times more aluminum than there is iron. And aluminum holds on to the phosphorus and doesn't let it go. And so once it's bound up in the sediments, it stays in the sediments and doesn't come back into the water column. So those are sort of our ABCs in a pristine lake. and now we're going to go to a impacted lake. So an impacted lake, we still have the warm surface water, but our inflow is bigger than our outflow. We're putting in extra nutrients. This is why Lake Smart is so important. Lake Smart helps to make this arrow a little bit smaller. All right, so it's less nutrients going in, so we're out of balance. These nutrients are out of balance. Now, if you fertilize your lawn or your garden, the plants grow. If you add phosphorus to the surface of the lake, the plants grow. And when the plants die, they fall to the bottom of the lake. So there we go. There's our plants falling to the bottom of the lake. And what they do is they build up in the sediments. And so what we have out in the middle of Great Pond and Long Pond is a compost pile. A really big compost pile. And that compost pile is food for bacteria. And the bacteria are eating that compost, and they're sucking the oxygen out of the bottom of the lake. So in an impacted lake, the oxygen doesn't increase in the bottom, it decreases in the bottom. And right now in Great Pond, we have about 30% oxygen left. And on Long Pond, we have about 20% oxygen left in the bottom of the lake because the compost pile is cooking along right now, and it's sucking out all of that oxygen. Well, low oxygen is bad if you're a fish, so the cold water fish are severely impacted. But the other reason we care about oxygen is it messes with our chemistry down here, and under low oxygen, the iron will dissolve. And so the iron will dissolve, we call that reductive dissolution, and when it dissolves, it releases phosphorus. So under low oxygen conditions, we get iron in the bottom water, we get phosphorus in the bottom water, and so that builds up. So that clock is now running. It just started about a week ago, and every day we're going to get more phosphorus and more iron in the bottom of the lake. And it's going to build up. And the consequence of that is we now have high nutrients in the bottom of our lake, and they're building up, and they're building up, and as they approach the thermocline, they leak. Okay, so they leak across that boundary. So now my nutrients are getting up here, and once they get into the sunlit, warm waters, that's when we have a problem. So that gives us our bloom. So that's what's happened on East Pond. On East Pond, the bottom water is actually only a meter thick. East Pond's only about 7 meters deep. And so what they do is they form a very ephemeral 1 meter layer of low oxygen water, and the water's actually pretty warm. So the phosphorus comes out of the sediments on East Pond really quickly. The oxygen on East Pond disappears about 10 times faster than it does on these lakes because it's warmer. That's not good.
Phosphorus gotcha.
I know what the problem is.
Oh, you have to plug it in?
I think in my family, this is referred to as the King theory of electromechanical failure. Usually it pops up and says, you're about to lose your screen in 15 seconds. All right, so what's happening at the bottom of the lake, I'm going to give my computer a chance to get a little bit of power, is that the phosphorus is now being released out of the sediments, comes up to the surface, and it creates the bloom. All right, so now what we want to do is we want to reverse this process. So we actually have 3 different ways we can fix the problem. 1, we can deal with the sediment. Dredge the lake. We have a compost pile on the bottom of the lake, suck up the compost pile. It's a great idea if you have a little pond. Not a good idea if you have a huge lake. It would be an engineering job about the size of the Big Dig in Boston. So we're going to cross off the list, sucking all the sediments out of the bottom of the lake. It's a great idea, but it's just not practical. So, second option is we don't have enough oxygen in the bottom of the lake. So, add oxygen. And we can do that relatively easily. About 20 miles of pipe in Great Pond, Huge reservoir of liquid oxygen on the side of the lake. 18-wheeler comes in once or twice a week. The oxygen boils off and we pump it out through pipes. And if you were a reservoir, if your job was to provide water for the city of Boston or the city of Washington, D.C., you would do that. And the nice thing about a reservoir is nobody lives around it, nobody fishes in a reservoir, nobody drives their boats in a reservoir, so all this pipe isn't really a problem. On Great Pond, it's kind of a problem. And so we're not going to add the pipe. So, I think we're getting there. The third option is to add aluminum. All right? So, Mike, he even came back. So, but my third option is to add aluminum. Let's see. So, this is what we want to prevent. So, here are my three options. High carbon, we're going to cross that one off the list. We're not going to dredge the lake. Low oxygen, we're not going to put the pipe in, but we could add aluminum. And by adding aluminum, we restore the ratio of aluminum to iron back to its natural condition. In a pristine, healthy lake, aluminum is about 10 to 20 times more abundant than iron. In our lakes, the aluminum is about twice as abundant as iron. We've shifted that balance over the last 30 years, and we need to shift it back. And we do that by adding aluminum. We do it carefully. You hire a company that does this commercially, and when they do it right, and they will, the pH doesn't change, they don't kill any fish, but they add a whole lot more aluminum to the bottom of the lake. So that's what we're going to do. And we're planning on doing that in East Pond either next spring or the spring after. So we now are in the permitting process with DEP to add $1 million of aluminum to East Pond. So now think scale, right? If it takes $1 million of aluminum to fix East Pond, it's, I think we may be a little bit optimistic that it would be $3 million on Great Pond. Might be a little bit more than that. Okay? So the idea is that you add aluminum. The aluminum now prevents the phosphorus from going into the deep water. So the phosphorus goes away. And if the phosphorus isn't going into the sediments, well, then these nutrients go away. Okay? And if the nutrients aren't building up in the bottom water, you're not leaking any more into the surface. And if you're not leaking any more into the surface, you fix your bloom. So that's the idea. And we'll know by the end of the summer whether this works. So if we add aluminum, and the plan is to add it in the spring, right after the ice goes out, they come in with a couple of barges, a couple 18-wheelers worth of aluminum. They come right into the boat launch, and it takes them about 2 weeks to spread it. With this sort of looks like a big lawn spreader, and they go up and down the lake and they drop the aluminum into the sediments. The oxygen will persist. It will still be low in the lake until you've actually burned up some of that high carbon. So it will take 4 or 5 years for the oxygen to return, but the phosphorus should be taken out in the first year, and if it works, the bloom should be fixed within about 6 months of adding the aluminum. That's the idea. Now, if you want to preserve your investment, you also need to deal with this inflow. So 10 to 15 years is the time window for an alum treatment, and you can go back out in another 15 years, and there's a lake in Maine that's having to do that, and that's going to cost you another $1 million. The other way to think about this is if everybody now doubles down on Lake Smart, right? This inflow shrinks, and now we shrink our inflow, and it's no longer an impacted lake. It is back to a pristine lake. So that's the challenge. The challenge is to understand the ABCs. Okay, what plankton is in the surface of the lake? How much oxygen is in the bottom of the lake? What is the chemistry in the sediments? And if you understand all of those components, you can figure out how much aluminum you need to add, when you need to add it, and have a reasonably good, let's say very good, probability of this working. So, the good news for East Pond is that they should be bloom-free after the addition of alum. The good news for everyone else is that we get this amazing test bed to demonstrate the effectiveness of adding aluminum. And then we need to then be very systematic in thinking about how we would apply this treatment to each of our lakes at the appropriate time for the maximum effect. So let's look at what's happening in Great Pond and Long Pond this year and last year. All right, so let's begin with sort of a big picture. These two easels right out by the bar are these figures. This is the depth of Great Pond, and the blue here is where the oxygen was below 2 parts per million, so right on the anoxic boundary in 1983. So in 1983, there was actually oxygen all the way to the bottom of the lake. And then we started building our compost pile, right? That compost pile had been building probably for 50 years. It just got to the point where we were sucking out significant amounts of oxygen. This is the lake today. Everywhere you see red, there's no oxygen on the sediments. So about 30% of the lake will be anoxic by the end of the summer. Let's look at it a different way. Let's look at a cross-section of what's happening in the lake. And this is 2016, because we're only halfway through the summer. So, spring, July, November. So, students are out as soon as ice out. They're working all summer, and then Brenda and Logan are out all fall taking measurements because the lake doesn't know that school has started on September 6th. Okay. This axis is depth. Whoops, went the wrong way. Okay. This axis is depth. So this is the surface, this is the bottom, and the colors are the temperature. So blue is cold and red is hot. This is called the heat map. And what we're seeing is at the beginning of the summer, the lake is mixed, top to bottom. And that's because the ice has gone out, the water's stirring, and it's all the same temperature. And then the lake starts to heat up, and as it heats up, it gets warm, it becomes red, and there's the thermocline. You can see the thermocline is the boundary between the red and the blue. And as those lines get closer together, it's like a topo map, that gradient is the most significant. So that's a barrier to mixing. And the green dots are actually the Secchi depths. And so that's the good news on Great Pond right now. The Secchi's pretty stable over the entire season. So, does Great Pond stratify? Absolutely. We have warm water at the top, cold water at the bottom. The consequence of this is that oxygen can't get from the surface to the bottom of the lake because you've got this boundary, this thermal boundary. So in the beginning of the season, this water's mixed, the oxygen's mixed, it's blue. So in this case, blue is high oxygen. And then the summer progresses. The deep water is now isolated from the surface of the lake, and the oxygen starts to go from 12 to 9 to 2, which is this yellow boundary, to 0. Okay? So that's the bolus of 0 oxygen water in the bottom of the lake, and 2, this sort of yellow piece, which goes all the way up to about 10 meters and lasts for about 60 days, is where we're releasing all of that nutrients. So we can build these for every year, but what we'd like to do is to have some metric to see how this is changing. And we call that the anoxic factor. And I'd be happy to talk to you about the mathematics behind calculating that, but it's basically the area underneath this blob, the area underneath this yellow boundary. So this is the anoxic data for every year where we have good oxygen data for Great Pond. And so starting in the early 80s, it was oxygen all the way to the bottom, so the anoxic factor was 0. And then sometime around 95, 96, we started to lose significant oxygen in Great Pond, and we got up to around anoxic factor of 6. That means that the entire lake was anoxic for 6 days. That's not right. Only about 30% of the lake went anoxic, so 30% of the lake went anoxic for 18 days, 18 or 20 days. And that's what's releasing those nutrients. These are the last 2 years. We're right around 7. And not all years are at 7. Let's see. We had some good years right around 2009. Actually, I think it was a particularly stormy year. And so we had wind events that mixed the lake. And as the lake mixed, we pulled oxygen down into the bottom of the lake. And so the anoxic factor wasn't as bad. So here's the bad news. I think that's what we're going to do this year. We're now losing oxygen 10 to 15% faster in Great Pond than we did last year.
Wow.
We're about 10 days ahead of where we were last year. Because the lake's been particularly stable. It's not been super warm, but it hasn't been very windy. And so what's happening is the lake's very well stratified, it's very stable, and things are the oxygen's disappearing in Great Pond. About 0.1 milligrams per liter per day. You only have 10 milligrams to work with, so you work it out, it takes 100 days to suck all the oxygen out of the bottom of the lake, and we're doing that about 10% faster. So this is my, well, it's not quite a WAG, but it's a gas, right? So that's where I think we are going to be this year. We're certainly going to be above 7, and we could be as high as 10. When you hit 15, that's when you have trouble. So at 15, you put enough nutrients into the lake that you start to get significant leakage up into the surface, and that's when you start to get blooms. Now, there's some hints that this is coming, and one of the hints is gliotrichia. Right? The gliotrichia seems to feed on the little bit of nutrients that get across. They seem to take advantage of it first, and I think people are starting to see blooms of gliotrichia, particularly on the north end of the lake, both on Long Pond and Great Pond, and that doesn't surprise us. The gliotrichia is going to come in first, and then the anabina is going to come in second, which is the blue-green that blooms on East Pond. If we add Long Pond data to this, now the purple points are Long Pond. This is the north basin of Long Pond. The south basin of Long Pond is quite a bit better. But the north basin is, again, right around 6 or 7. It's a little bit more variable, and there's clearly one year back in the 90s where things were a little bit worse, but we're still seeing this sort of trend. Better in the early years, sort of increased around 1990 to 2000, and then we've been hovering somewhere around 7 or 8. And I was talking to Pete Callan as we got here, and it looks like Long Pond is, well, anoxic right now. So Long Pond went anoxic when he sampled yesterday. So there's no oxygen in the bottom of North Pond, the north basin of Long Pond. But at the rate at which it's disappearing is sort of on track with last year. So the message is Long Pond's about the same as last year. Great Pond's about 10 to 15% worse. So what does that mean? Well, you put more nutrients in the lake, you grow more plants. You grow more plants, the water becomes less clear. And do we see evidence of that? Well, on Great Pond, not yet. Maggie said it's the best water quality you've seen in years. And she's right. This is date for 3 different years. So it's April, July, November. This is depth. There's my Secchi disc. And on Great Pond, the Secchi transparency is around 6 meters. That's great. You can see the bottom, 18 feet of water. It's really good. The blue is 2015. The red was 2016, and the green is 2017. So we haven't seen the bloom yet. But remember East Pond. East Pond was fine until 1989, and then it bloomed. And then it bloomed pretty much every year from that point on. So the goal is to keep it looking like this, not wait till we have a problem before we act. And the Secchi will get worse over the course of the summer. How much worse, we'll have to wait and see. So there's sort of 2 thresholds that we should consider. 4 meters, which is where you start to notice the decline, and 2 meters, which is the Department of Environmental Protection's definition of an impacted lake. And East Pond is there, okay? Salmon is there, and we don't want to get to 4 meters. So one of the things that this group and every other lake association is going to need to wrestle with are what are the warning signs? What is the line in the sand where you go from talking about water quality to doing a much more proactive step? So think about the milfoil story. Early action, early intervention helped to head off a major problem with milfoil. And one of the things we need to talk about is what's the next step for these lakes. Let's look at Long Pond. Long Pond has a similar, stratification. There's the warm water at the top. A lot more oxygen coming out of Long Pond. This is the north basin of Long Pond. It tends to catch all the stuff coming over the dam from Great Pond. And one of the things I should mention is these numbers right here. These numbers are the phosphorus concentration in the bottom. Remember I said 8 to 10 is sort of the threshold? And we're up 8, 10. That's really good up here. That's 100 parts per billion at the bottom. Right? So we got a lot of phosphorus coming out of the sediments. And the good news is it doesn't quite make it to the surface. Well, it sort of does. That's why this is going up like this. Right? So this is the Secchi for Long Pond. It's banging around. It's pretty good, 7 meters. But every year it starts marching up. and it marches up almost to 4. The good news is nobody's out there boating in November, right? So right now, the bloom that we see every year, A, it's not bad, and B, it's very late in the season. But you can imagine what happens when this marches over to here. Right? Then you start to worry. And you really want to get down to the dollars and cents. For every meter you lose in Secchi transparency, you lose 20% value in your house. So the economists have figured this out. They've done the hedonic model. Every meter you lose in Secchi transparency, you lose about a 20% property value. Now, not when you go from 6 meters to 5 meters, but you start going 5 to 4 or 4 to 3, and it's not a perfect linear relationship, but it is real. All right, so should we be alarmed? Yes. East Pond and Salmon Lake have already bloomed. They almost bloom every year. And salmon, you should go over to salmon sometime, middle of August. And ask yourself, would you swim in this lake? Most people would say no. Great Pond will likely set a record for Anoxia in 2017. It's 10 days ahead of schedule. It's certainly ahead of any data that we have. I don't think it's going to bloom this year, but it's certainly moving in the wrong direction. So that's sort of the bad news. But this is the good news. The good news is we're all sitting here and there's 190 people that came to this meeting. And we actually have a way to deal with this. This watershed, these 7 lakes are probably the best studied group of lakes in the state of Maine, maybe in New England. We're measuring the oxygen, we're measuring the nutrients, we're measuring the plankton abundance, we're measuring the Secchi transparency, we're talking about it, we're pulling all the data together. We have a merged conservation organization that is working on the in-lake work, the shoreline work, the upland work, and they're doing it in a concerted way. And then, so that's sort of, this part, scientific knowledge, limnology, ecology, modeling. We're full in on this. We also have a deep sense of history and sense of place. People are very much attached to these lakes. And that attachment means that they're they're committed to solutions. And then finally, we've got this community involvement in action. And so this was actually the logo for Maine Lake Society meeting a few years ago, the delicate balance, but it is a delicate balance. That's the good news, is that we actually now are in a position where we understand that delicate balance well enough that we can pull the levers to keep the lake the way we want. We can restore East Pond, we can restore salmon, and if we're diligent, we can keep Great Pond and Long Pond from ever blooming. So now the community piece is defining what is the metric to success. You want the lake to look like it did in 1950? Would 1980 be okay? Would holding the line at where it is today be okay? That's the kind of decision that the community has to make. And that's not something that the scientist group, there's going to be a science advisory board, Lynn mentioned that. That's great. And we'll run the models and we will run the scenarios. But in the end, it's the people that live around the lake that are going to have to make the decision as to what actions they are willing to take. And this is also very encouraging, right? Those are the lemonade salespeople, right? Earning the money for the BLA to help you preserve the lake. And with that, I'll take questions. We'll go here and there.
So I'm aware that in the northwest corner of the south half of Long Pond, the place that we
The northwest corner of the south half of Long Pond.
right down there.
Okay.
The stream that people often call to Lost Pond, that has big vats of floating green crap and
Looks
salt.
like
green crap.
green crap or like green cotton candy.
Right, with bubbles of something underneath it. So has anybody figured out what's coming into there? Because in my knowledge, this is new this year.
Yeah, so the general description of that green slimy stuff that looks like cotton candy is metaphyton. Meta meaning big. And it's growing on the sediments. And because the sediments have phosphorus in it, it's pulling the nutrients right out of the sediments. And it doesn't actually always grow in areas where it's deep and has low oxygen. It seems to do okay in the well-oxygenated sediment. So I don't know why we're seeing it in that particular place. It does tend to roll up like a log, and so